All right, welcome back, everybody. I made the brave and ill-advised decision to rearrange my slides over the lunch break, so hopefully that didn't introduce any problems. Previously, I said we were going to spend this lecture deriving non-contextuality inequalities, but I decided this topic fits a little better with what we just discussed, so I'm going to discuss this first, and then we'll do non-contextuality inequalities, some explicit examples, in the next lecture. So in this lecture, I want to sort of synthesize non-contextuality with the process theoretic approach that John went through. And this is essentially a way of making more mathematically formal the things that I sort of set up piece by piece in the first lecture. So as John talked about, you can view an operational theory in the sense that I discussed in the first lecture as a process theory together with some rule for making probabilities. So the process theory has system types, which are just kind of abstract degrees of freedom, like a photon or an electron or something. And the processes in an operational theory are just laboratory procedures that you apply on these photons or electrons or other systems. So we can kind of depict those lists of lab instructions we talked about as just some list inside a box, and we can depict things pictorially within a process theory. And whenever you get a closed diagram like this, the probability rule can be applied to tell you the probability of distribution over the outcomes, in this case E1, conditioned on the things that came before. And as John also talked about, once you have this notion of an operational theory, you can define operational equivalents of two procedures. So I talked about specific cases for preparations and measurements. This is the completely general case. We can depict an arbitrary process in this form. Of course, these systems might be trivial, maybe they're composite systems, so these diagrams really capture any possible diagram that you can draw. It can always be just viewed as some kind of transformation. And we say that two transformations are operationally equivalent if and only if, for every closed circuit you can draw, you get the same probabilities. And really, I should have drawn the probability rule being applied to these diagrams, because strictly speaking, they're not probabilities until you apply the probability rule. But so if they lead to the same probabilities for all circuits in which they can be embedded, then T and T prime are operationally equivalent. And John motivated in his lectures that the most general circuit you can draw is one of this form here with this kind of side channel. And then you can lump together all your processes, all these transformations, and all their special cases, states, effects, circuit fragments. You can lump them together into equivalence classes, and you can label each process. So here I'll label the process T by its equivalence class and its context information, like John said. All right, and then we can talk about the quotiented theory. So we can quotient with respect to this notion of equivalence. And so we define a quotienting map, which takes our process in the operational theory, and it maps it to a process in a quotiented theory, which just throws out the context information, and it just is a representation of the equivalence class alone. And as I think John mentioned, this is a diagram-preserving map, so we can depict it with this kind of shaded map like John talked about. So the application of the quotienting map to this process in the operational theory is depicted like this. The result of that application of the map gives you this process here in the quotiented operational theory, also known as the GPT. Okay, so we have these two kinds of operational theories, and we're interested in representing both of them, or trying to find explanations, classical explanations, for both kinds of theories. And those explanations will be slightly different precisely because these kinds of theories are slightly different. So we have the unquotiented things, which often are called operational theories, and the quotiented ones. Okay, so what do ontological representations look like for these theories in a more process theoretic way, so in a way that's defined for kind of arbitrary circuits? Well, an ontological model of an operational theory obviously has its domain being the operational theory, viewed as a process theory, and it has as its codomain substock. So we're trying to find a representation of the transformations in the operational theory as substochastic transformations. So we start with this kind of object, again labeled by its equivalence class and context, and we're trying to find a substochastic map, which in principle can depend on both the equivalence class and the context, which is just mapping semantic state space for the input to semantic state space for the output in a way that's described by a stochastic map, which in general might be subnormalized. And this, for this to be a valid, physically meaningful ontological model, it has to satisfy a number of properties. So first of all, it better reproduce the predictions. So when you wire together these operational processes in some big circuit, it better be that the wiring of these stochastic processes gives you the same expected predictions. It has to represent ignoring appropriately. So this is a fairly obvious constraint that just says if you ignore a procedure in the operational theory, the representation of that in the substochastic process theory better just be marginalization over the appropriate system. And then there's two more assumptions, which I'm not going to focus on too much here. The first is diagram preservation, that the circuit in the substochastic image of the map has the same structure as the circuit in the operational theory. And it has to respect convex linearity, which is these assumptions I'll come back to in the final talk, why we need these assumptions, in case it's not clear. And I'll just, as I kind of mentioned before, I'll note that as special cases of these definitions, well, if you consider the case where there's no operational input, then by diagram preservation, there will be no substochastic input here. So you're mapping an operational state preparation procedure to a stochastic process with no input, which is to say just a probability distribution, which might be subnormalized. So we recover the case for states. We recover the states for effects similarly. And recall that we said there exists a non-contextual ontological model of an operational theory if and only if there is an ontological model of the associated GPT. So now, clearly then, we need to, if we want to extend this was all done for prepare measure in the talk earlier. Now we want to extend all this to the full process theoretic framework. So we need to define what an ontological model of a GPT is. So the difference here is the domain of the map, right? Before, the map we were interested in was an operational theory, unquotiented. Now we're dealing with the case where the domain is the quotiented operational theory. And everything is pretty much the same, other than the domain of the map, right? We're taking GPT transformations now, and we're trying to map those into the substochastic process theory. And critically, the one thing you need to note here is that this process here, because it's now living in the quotiented theory, it has no context information. So clearly then the representation can't depend on any context information. So this is precisely why it doesn't make sense to directly apply non-contextuality to a GPT. But as we mentioned, we have that nice equivalence between the two concepts nonetheless. Okay, so I think it's nice to see what this looks like still a bit schematically, but imagine you have some complicated GPT circuit with some states and transformations, and this can be arbitrarily complex, but you've got GPT systems and GPT processes on them. What does an ontological representation of that look like? Well, it looks like exactly the same thing, except that these processes are now stochastic maps, and the systems are just classical random variables. So I find this very compelling. It's this incredibly naive notion of classical explainability. You say, why don't you take your GPT circuit and just try to make everything classical in the usual boring sense of random variables and stochastic processes on them. And if you can find such a representation, then you can think of it as a classical explanation, and it turns out to be equivalent to this notion of classicality that was motivated in a very different way from Leibniz's principle and from the consideration of the geometry of GPTs and so on. So I feel like this is a very compelling picture. And it's closely related to a third kind of representation, which has been studied in the quantum optics community. These are known as quasi-probability representations. So historically, these have been defined as maps from density operators and POVM elements to real functions over some space of classical states. So a famous example of this is the Wigner function. So you compute the Wigner function, which is a function of two real variables, x and p, where you take a given quantum state rho, and you represent it by taking this complicated function, which just returns a real value for each x and p. And similarly, you can represent Hermitian operators using this, and then you can compute probabilities from these two using classical probability theory. And the problem with these approaches is that they have no real physical significance in general, because in general, these real values here go negative. For some quantum states and for some effects, these values go negative. Now, if it so happens that they go positive, then you can think of it as a sort of classical probability theory as an ontological model, and you can ascribe some physical significance to it. But in general, these are sort of just mathematical representations, not physical representations. And there's many different Wigner representations. There's like the Glauber-Sudarshan representation and the discrete Wigner function that Gross defined, and many similar quasi-probability representations. And these have been used in quantum optics quite a lot and in quantum computation. And negativity in these is often thought of as an indicator of non-classicality. And we can kind of make that precise using the things we've been talking about. So to formalize a quasi-probability representation, we can formalize it in exactly the same way as the other two representations we just talked about. Now what's changing, while the domain is still the GPT, the thing that's changed is the codomain. So we see instead of substock, we have quasi-substock, which is essentially defined in the same way, except that now the matrix elements of those processes don't have to be between 0 and 1. They can go negative as well, for example. But other than that, it sort of satisfies all the same properties. And as I alluded to earlier, if it so happens for a particular subset of quantum theory, maybe the specific experiment you're looking at, that you can find such a quasi-probability representation which happens to be non-negative for all the processes of interest, well then, essentially, you're finding that the image of the map is really living within substock, and so it's also an instance of an ontological model of a GPT. And that's precisely the case in which you can ascribe some physical significance to this kind of representation. So again, we sort of have the same picture where you know, whatever circuit you're considering, quantum circuit, GPT circuit, whatever, you try to find an analogous circuit where you have classical random variables instead of GPT systems, and the processes now are matrices, which are like substochastic matrices, but they can go negative. And the nice thing about quasi-probability representations is that these always exist. For any GPT, for any circuit, you can always find such a representation, but generically, these representations involve these negative matrix elements that I mentioned. And so then you can ask, you know, when is it possible to find one which has only non-negative elements? And that's a notion of classical explainability, which, as we've said, is sort of equivalent to the other notions that we've discussed. So I'll just summarize this now all on one slide. If you have an operational theory, that defines a GPT by quotienting with respect to operational equivalence. And you can say that there's these 4 equivalent notions of classicality for the operational scenario. So first, if it admits of a non-contextual model. Second, if its GPT admits of any ontological model. Third, if the GPT admits of a simplex embedding. And fourth, if the GPT admits of a non-negative quasi-probability representation. And so some of these are, you know, quite closely related by their definitions, but each one has a slightly different perspective, and sometimes one perspective is more useful than the other. So you can pick which one of these. You know, all these different notions, they differ by the precise domain and codomain of the map, and sometimes one of those is easier to use to prove whatever you're trying to prove. So for example, in the next part of the talk, I'm going to prove a theorem which says that all quasi-probability representations of GPTs, when you study the structure of transformations and you go beyond the prepare-measure case, they all have a very simple mathematical structure. And because of these equivalences, it follows that so do all non-contextual ontological models. They also have this simple mathematical structure. The only difference is there's kind of a quotienting operation involved as well. So henceforth, I'm going to focus largely on quasi-probability representations, but you can keep in mind this equivalence. That's really what's motivating us to care about these representations. So recall that a quasi-probability representation is a diagram-preserving linear map from a GPT to quasi-substock. So we start with our GPT vector here, and we apply this representation map. Because it's diagram-preserving, I'm going to use that notation that John introduced of applying this kind of shaded map, Xi, to the GPT state. And now I'm viewing systems here as associated with the vector space of real-valued functions over the ontic state space lambda b. So earlier I was labeling these systems just by lambda b and thinking of that as a classical random variable. This is just a slightly different mathematical formalization of the same thing, which will turn out to be a little more useful later on. So instead of labeling it just by the ontic state, I'm labeling it by the set of real-valued functions. So this is the vector space in which the epistemic states live. It's the vector space in which the response functions live. So in particular, this object here then is just equal to a function on the a real valued function on the ontic state space of B. So such a function, because it has no inputs and it has an output, it's just a probability distribution in the case where they all happen to be positive. In general, they can go negative, though, because we're doing quasi-probability representations here. OK, so just to make sure everyone's clear what we're saying here, we have some quantum states, maybe this state or this state. We're mapping those into, again, real valued functions over the ontic state space. So here's an example. Here's a different example of objects of this sort here, equivalently objects of this sort here. OK, and the reason I'm being so slow and pedantic here, and also the reason why I chose this particular formalization of what a system is in quasi-substock, is because now we can see that what this map does ultimately, well, it's just a linear map from one real vector space, the one where the GPT states live, to another real vector space, the one where these response functions and epistemic states live. So now we can kind of change our perspective a little bit. Instead of viewing this representation map as a map between one process theory to another, the GPT process theory to the process theory quasi-substock, we can view it in a different way in a sort of larger super process theory, which contains both the GPT and quasi-substock as special cases. So let's define that larger process theory. I'll call it R linear for real linear vector spaces and linear maps. So this is the process theory where the systems are real vector spaces, which subsumes as a special case B, the real vector space in which the GPTs live, and it subsumes this real vector space of functions on the ontic state space. And the processes are just linear maps on these systems, on these vector spaces. So the advantage of this approach is that now, instead of representing this as a diagram-preserving map between these two different process theories, we can view it just as a linear map within this single linear map within this larger process theory, R linear. So in particular, let me just redraw this diagram as follows. Instead of a diagram-preserving map C applied with this kind of shaded box, now we just have a GPT state. We apply a linear map to it as a process, just in the usual sense of composition within a process theory, and we end up with exactly the kind of process that we wanted, which is a vector in this quasi-substock process theory. Does that make sense to everyone? It's just an equivalent way of representing things within a kind of larger process theory, rather than as a map between two process theories. It's kind of just bookkeeping, if you like, but it's going to be useful for us. And just a cute thing to note, this chi map here is really just the simplex embedding map that was in the definition of simplex embedding of a GPT, because it's taking, okay, if you can find such a map where everything is positive, then it's just an instance of a simplex embedding map, because it takes your GPT states and it maps them into valid epistemic states and response functions. So that's a nice little connection. So that was all for states. Now for effects, it's the same story. We can represent things either as a diagram-preserving map between two process theories, or we can represent it as a process within the larger process theory, R linear. Either of these works. They're just two different ways of representing the kind of map that we're interested in. Now, it has to be that this phi process here is somehow related to this chi process, because they're both coming from this single diagram-preserving map. So what's the relationship between phi and chi? Well, for starters, we can show that phi is the left inverse of the chi process. So consider a composition of a GPT state with a GPT effect like this. And within the ontological representation, what is the representation of this scenario? Well, just apply the representation map. Now we use diagram preservation, which says that we can first represent the state, the GPT state, and then represent the GPT effect, and then compose those two within the within quasi-substock. So that's just diagram preservation. And then using what we just showed on the previous slide, we can reimagine this application of this diagram preserving map as the application of this chi process, and similarly for this diagram preserving map on the effect. That was the phi process that we introduced. And now note that this equality has to hold for all effects and for all states in the GPT. So by tomography, it follows then that the process in between this state and effect, which here is the identity transformation, right? There's nothing in between these two, has to be the same as the process between the state and the effect here. So the composition of chi with phi in this order has to equal the identity process, like this. So we see that if you apply chi and then you apply phi, you get the identity. That just means phi is the left inverse of chi. Okay, so how can we use all this to talk about the representation of transformations, right? We're trying to make this all completely general, not focus on preparations and measurements. So there's a fact about a certain class of GPTs, which we're now going to appeal to, and I'm not going to prove this, but you can ask John about it if you're interested. So there's a class of GPTs which are said to satisfy the principle of local tomography. And what this means is that if you have a bipartite state or a bipartite transformation, and you want to characterize it, you don't have to actually do bipartite measurements and bipartite preparations. You can just locally probe each of the inputs individually, look at all your statistics, and you can figure out what that process is. In some GPTs, this isn't true. If you want to completely characterize a process, you have to sort of jointly prepare all the inputs and jointly measure all the outputs. But in GPTs where you don't have to do that, we say that they satisfy local tomography. And in these GPTs, there's a really nice property that you can decompose any transformation into a linear sum of states and effects in the GPT. So this transformation in the GPT can be written with some matrix coefficients here in terms of an effect followed by a preparation indexed by the matrix elements. And so this is kind of like decomposing the identity operator on a Hilbert space, but it's not really quite the same because this matrix M here is not the identity matrix. It can be very complicated and ugly because there's no orthonormal basis of density operators and POVM elements for the quantum example, and similarly for arbitrary GPTs. But in any case, you can find some real matrix of coefficients where this decomposition holds. And I should also say this class of GPTs is sort of, it's a pretty standard one. It's a very large class that subsumes most of the things people study, certainly classical quantum, Speck and Toy theory, most of the foil theories. But there are some that don't satisfy this. So everything I say will be now for this class of GPTs with this property. So let's use this property now. So if we're interested in the ontological representation of a given transformation, well, we can just substitute that decomposition of the transformation. And now, by linearity of the map, we can just pull the sum and these constant coefficients out. And then we can apply diagram preservation to say the representation of this effect reprepare channel is just the representation of an effect, and then separately the representation of a state. And so this is already a pretty nice insight. It says in this very large class of GPTs, the representation of transformations can be completely constrained, it is completely constrained, by the representation of the states and the effects. So you might have thought there's going to be a whole bunch more information in figuring out what happens to all the transformations in your theory. But for all these GPTs, actually all the information somehow is encoded in the way you represent the states and effects. So that's a pretty powerful constraint, and maybe an interesting insight that deserves further thought as well. Now, we can go further using that kind of bookkeeping change that I mentioned. So we can rewrite the diagram preserving map on the states in terms of the chi map, and the diagram preserving map on the effects in terms of the phi map. And I could have called this chi inverse because actually not. At this stage, we don't know that they're actually each other's inverses. We only had the one direction of the inverse. So that's why I'm still calling it chi and phi. But remember, these are related by a property. And then finally, notice that this stuff in the middle here is just t, right? This was the way we decomposed the transformation in the first place. So we put t back in by kind of undecomposing. And so we see that the representation of a transformation is governed by the same chi and phi maps that were that were telling us how to describe states and effects in the ontological model. And you just pre-compose with phi and post-compose with chi. So now we just want to find what's the structure of these chi and phi maps. Right now, I haven't told you much. They must exist. They're linear. But we can go a lot further. And And the first thing we can note is that they really are actually inverses of each other. So we can prove that by now considering the representation of the identity transformation. So we apply the diagram-preserving map to the identity. Well, remember, that's just pre-composing with the identity phi and post-composing with the identity chi. That's what we just proved. And furthermore, by diagram preservation, the representation of the identity in the GPT should just be the identity in quasi-substock. So in other words, we have that the identity channel is equal to phi followed by chi. Earlier, we said the identity channel on the GPT was chi followed by phi. So now we see that these two maps really are each other's inverses. And finally now, we can actually find an explicit form for this chi map and the chi inverse map in terms of a basis for the GPT. So the way we do that is, let's take the chi map, and let's just introduce an identity decomposition for the system in quasi-substock. So this lambda effect is just the response function, which is 1 on lambda, and it's 0 on all the other lambdas. And so this is sort of the simple kind of decomposition of identity, because if you like, it's in the classical theory. It's not in the GPT. So this is the decomposition of identity. And now we can just notice that this whole composition here is just some GPT effect. Now, it might not be a physical GPT effect. It might be non-physical, but it lives in the span of the GPT effect. So it's some process of this type with a GPT input and with no output. And we can just call that process d lambda a, because it depends on chi and it depends on lambda. So we'll denote it like that. And I'll keep this coloring around just to kind of remind you where it came from, but maybe it'll also help you remember that this can be a non-physical process. OK, and you can just check for yourself that this set of operators, D here, spans the space of effects. So it forms a basis for the vector space of effects. And so I'll just collect this together, and I'll refer to it as a basis sometimes. It's a basis that's indexed by the ontic states lambda, or which only really can be interpreted as ontic states when everything happens to be positive. So really, maybe you should just think of it as a classical sample space. But we're labeling it suggestively again, because we're really interested in the case where you can find these non-negative representations. So we can do all the same things for the effects. So we can take chi inverse. We can, again, apply the identity decomposition on the classical part of chi inverse. And then we can lump together these two to just get some possibly non-physical GPT vector that's living in the span of the GPT states. And again, you can just check that this forms a basis. It's a spanning set. And you can also check that from the invertibility, from the fact that chi is equal to chi inverse, well, that should tell you that there must be some relationship between these two bases, right? You can just apply chi to chi inverse, and you better get the identity. The only way for that to happen is if the composition of these two in the GPT is just given by the Dirac delta function. And you can furthermore show, just from sort of the fact that normalization has to work out the way you expect, that if you trace out one of these state vectors, then you get just the value 1. And if you sum over lambda this set of effect vectors, you get the marginalization, or the GPT unit effect. So this is kind of what you'd expect to come out of normalization, right? This looks a lot like saying that a quantum state is normalized. This looks a lot like saying that the sum of the elements in a measurement have to be just the identity. But remember that these are non-physical, so it's kind of the non-physical analog of those constraints. So in conclusion then, we have our transformation. We want to represent it in the ontological model. We can do that in terms of pre and post composition by chi and its inverse. And now we substitute for chi this explicit form where we have a sum over lambda, in this case lambda prime, of the application of this GPT effect with that state in quasi-substock. And similarly here, we have this sum over lambda being substituted for chi inverse. And now, if you look at this, this is a closed diagram within a GPT, right? So it's just a real value. So this here, what we end up with is a sum over some real values indexed by lambda and lambda prime, which just defines a matrix within quasi-substock. So these real values might not be non-negative, but this is just defining a matrix within quasi-substock by some matrix coefficients in terms of the basis, the two bases that we found. And every diagram-preserving quasi-probability representation has this specific form. So maybe it's useful to see what this looks like in quantum theory. This is just a special case of that fact that we just proved. So you can always construct your quasi-probability representation following this methodology. First, you pick a basis of trace 1 Hermitian operators. So a basis for the vector space of Hermitian operators on your Hilbert space. You take that basis and you compute the unique dual basis satisfying this property, which I said follows from invertibility. So that it turns out that this basis is always unique. There's always some single set of d lambda operators which satisfies this property with respect to the f operators. And people sometimes call these the frame operators, and this is the dual frame operators, which is why they're f and d, and maybe I'll use that language as well. So now, from this frame and its dual, you compute the representation of the states by just taking their trace as quantum states with the dual frame operators. For each lambda, this just gives you a real value. So this is a vector of real values indexed by lambda. Similarly for the effects, but now you take the trace with the frame operators instead of the dual frame. And then for transformations, you do the kind of obvious thing. You apply the transformation on the frame operator, and you trace it with the dual frame operator, and you get out a matrix of real values indexed by lambda and lambda prime. So this expression we just saw is the algebraic version of this diagram. Right? You take your transformation, you apply it to the frame operator, you trace with the dual frame operator. That gives you these matrix coefficients here. And this mathematical construction has been studied in the literature and in mathematics. It's called a complete frame representation. And so many properties are known of these things, and you can use those properties to help you out. OK. Any questions so far? Great. So now you can hopefully have some idea of where these diagram-preserving maps are useful and how you can use them in some proofs. And now, if you find such a quasi-probability representation with this kind of structure that we've talked about, where furthermore it so happens that all those matrix elements are non-negative, then, as we've said many times, this will be a valid ontological model. If instead these processes necessarily go negative, for every possible choice of frame, you have to check all the frames. You can't just check one. But if it goes negative for all possible frames, then, OK, here what I've written is if you pick one particular frame and you find that it goes negative, then this particular quasi-probability representation is not an ontological model. If you find that there's no choice of basis for which the resulting processes are non-negative, then the scenario doesn't admit of any ontological model, because they all have to have this form, which start from picking a basis and then following this construction. So this is, again, a way of getting proofs of the failure of classical explainability. And of course, again, then non-contextual models have to have the exact same structure, but where you first quotient, and then you pick a frame, and then you do the construction. And some of the familiar examples of quasi-probability representations that you've seen have exactly this structure, of course, because they satisfy the assumptions in our definition of quasi-probability representation. So the Wigner representation is exactly a frame representation in the sense that I just showed you. And the Speckens toy theory, maybe it's not obvious from what Matt presented, but it also has exactly this form, where you pick a particular basis. So this is kind of like the P and Q are like the two axes in the, you could think of it as like the number and phase for the one case that he was considering. And together they form the ontic state space. P and Q together form an ontic state. And you can define a set of Hermitian operators like this complicated looking thing, where I haven't really actually told you how these W's are defined, but under the appropriate definitions, you just compute the representations of the quantum states by tracing them with these operators. And what you find is if those states are stabilizer states, then these things all happen to be positive or non-negative. And so what you get out, furthermore, are the precise values of the Speckens toy theory. So for dimension 3, you get out all these for the different quantum states in the stabilizer subtheory. So it just follows a construction of this sort. I won't go through those details here, though. And this representation in this kind of more algebraic approach was independently constructed by David Gross. And so it's sometimes called Gross's discrete Wigner representation. And like I said, it follows exactly this complete frame representation approach. And it's exactly the same thing as the Speckens toy theory. They're just different ways of formalizing the same thing. And you can do this for correlated states as well, just by taking kind of tensor products of these operators and then tracing with those. Okay, but I want to now move on from these examples, and I want to point out some more useful properties. So remember, this set of frame operators forms a basis. So it spans the GPT vector space, and it furthermore has to be a minimal set. So they all have to be linearly independent. So it follows then that the number of elements in the set is exactly the dimension of the GPT. And this set is indexed by the ontic states, right? So the number of ontic states has to be the same as the number of elements in the frame, which has to be exactly the dimension of the GPT. So suddenly, we have this massive restriction on the scope of possible hypothetical ontic state spaces if you're committed to non-contextuality, or equivalently just to there being an ontological model for your GPT. Then the number of ontic states, when you consider transformations, has this really strong restriction. And so for a qubit, for example, the GPT dimension is 4. So the number of ontic states in a non-contextual representation of a qubit is going to be at most 4, which might sound familiar. Looks a lot like Speckens toy theory, right? In contrast, we saw another ontological model which had way more ontic states, right? A continuously infinite set of ontic states. And this model is ruled out just by the structure of the transformations on a qubit, and together with the assumption of non-contextuality, if you like. So you can learn something about sort of the physical, the scope of possible physical properties in the world by this assumption of non-contextuality. And I'll just note that if you don't consider the structure of transformations, you don't get this strong bound. At least no one has shown how to prove it yet. You rather get that the number of ontic states can still be bounded, but it's the GPT dimension squared, which is that same dimension that I said. That's how high a simplex, that's how high a dimension you have to look for simplex embeddings, precisely because of this result. Okay, so these kinds of results are useful because they give you new tools for proving non-classicality, right? If someone comes to you and says, I've built this model for a qubit, I think it might be a good non-contextual explanation, and you say, but wait, your model has 8 ontic states, well, then you know immediately that it will be transformation contextual. It might be prepare and measure non-contextual because 8 is less than 16, but it won't be transformation non-contextual. And there exist such models, so you can actually use these results at that sort of practical level. Okay, so what do we do in the face of the fact that when we go and we look at the world, we see that the world is, in fact, not described by a non-contextual ontological model, right? You derive some inequalities, as we'll do in the last lecture. You go test them, and you see they're violated. So does this mean we should give up on non-contextuality and just say, well, Leibniz's principle, it worked well for Einstein, but it's not working for us, so we should just give up on the principle? Should we give up on realism? Should we say, well, maybe the ontological models framework was mistaken. We should stop trying to provide explanations of data in experiments, and we should just stick at the operational level and not worry about kind of causal explanation. Well, I think that's also a bad approach. I think causal explanation is kind of what drives us as physicists and as humans, for that matter. So what we propose in this talk and this paper is we should try to hold on to something like the ontological models framework, but modify it in some way. So we need to keep on searching for realist explanations, but we have to revise them a little bit in such a way that we can hold on to Leibniz's principle, and in such a way that we can hold on to locality. Because you could ask the same questions for Bell's theorem, right? Do we need to just give up on locality and accept that there's instantaneous superluminal influences? Well, if we can come up with a nice notion of realism that still allows us to give good causal explanations, but which violates some of the implicit assumptions of the ontological models framework, then we can get around these no-go theorems. So let me say a few words about that, this nascent approach that you can find in this paper. So it's very much in the early stages, kind of speculative. But so the problem with modifying our notion of realism is there's kind of good reason why this has been the standard notion of realism for so long. It was kind of just implicitly used by Einstein and Bell, and anyone who was thinking about kind of trying to find explanations for quantum theory. This is the way that we usually think about the world in our kind of intuitive classical macroscopic selves. And if you start trying to modify it, it's easy to just go so radical that nobody's really, you don't end up with a compelling interpretation that can kind of convince the rest of physicists that it's good. So like in many worlds, it still purports to be a realist kind of explanation, but it's unclear how you get any kind of causal explanation out of many worlds, and it requires you to believe in this multiplicity of worlds. It's a very radical interpretation. And so similarly with other attempts to maintain realism, they typically give up on some really strong features that we'd like to hold on to. Like in cubism, you give up on kind of observer independence, and there's no like objective world outside of that's kind of universal to all observers. So we need to have some guiding principles, otherwise you can just go wild. And we want to have some constraints on what kinds of realist interpretations do we think are interesting. And pretty much everyone that I know agrees that locality is a good principle. If you can seek realist explanations that are local, that's preferable to seeking those which are not. And so all of these purport to be local realist explanations. But from our perspective, as I've already said, we want also to look for realist explanations that allow you to be non-contextual, or to satisfy Leibniz's principle, if you like. And we're also motivated to unscramble causation and inference. And this is something I don't really have time to get into. It's in this paper again. But it's these two latter guiding principles which kind of distinguish the approach that I'm about to tell you about from these other approaches to coming up with non-classical realist frameworks. So where we take our inspiration from is we think of ontological models in a particular way. We basically think of them as classical causal models. And there's two kind of key components. The first is the kind of diagrammatic component. When you draw a diagram, it's kind of it's a hypothesis about the causal structure in your scenario. So in the Bell case, we have this common cause causal structure. That's the kind of causal explanation we're looking for. And there's kind of rules for how you do classical causal modeling, which I haven't gotten into, but they're relatively well established and well understood. And similarly, there's kind of the probabilistic component. So the way that you make inferences in the face of uncertain knowledge. So this is sort of all about what's actually existing in the world and how it evolves dynamically. And this is describing how agents reason about what's happening in the world when they don't have complete information. And the ontological models framework, we view it as sort of a synthesis of these two in a sense that we make precise in this framework, which we call the causal inferential framework, because we have the causal stuff and we have the inferential stuff. And what we'd like to do is we'd like to find some non-classical generalization of the theory of classical causal models. And this is kind of a hot topic in quantum foundations these days. I think it was the topic of one or both of the previous Solstice events. So if you're interested, there's probably some recorded talks on that. So people are working on sort of intrinsically quantum causal models. And similarly, people in the past have worked on non-classical theories of inference, so things like quantum logic. If you can find some suitable generalization of these classical notions of causation and of inference, and then you synthesize them together in the same way that we built the ontological models framework out of these two notions, then our hope is to construct a process theory which contains both the sort of the description of what's happening in the world and the description of how you reason in the face of ignorance, but in a way that's kind of intrinsically non-classical. So this is kind of like these non-classical notions of causation and inference stand in relation to the classical ones in the same way that relativistic notions of space and time stand in relation to the pre-relativistic notions of space and time. And they allow you to maintain consistency. Our hope is, if we find the appropriate sort of process theories describing these non-classical notions, they'll allow you to avoid these no-go theorems and avoid inconsistencies in the same way that the relativistic notions of space and time allow you to avoid what would otherwise be inconsistencies with respect to the usual notions, like the two postulates of special relativity seem in contradiction when you first hear about them. To understand how they're not, you have to go to these relativistic notions. And then you see, oh, there was never a no-go theorem that you could make. You just had to notice that you give up on these implicit assumptions. Similarly here, we have all these no-go theorems, but they rely on these implicit assumptions, so those are the ones we want to give up. So the notion of realism that we're trying to salvage is that statistical correlations should have causal explanations, and our goal as physicists is to find those. The problem is Bell and what I've been focusing on, non-contextuality, no-go theorems. And the idea is, by allowing these new notions of causation and inference, one can search for causal explanations which satisfy the spirit of locality and non-contextuality. I say the spirit because, strictly speaking, these two notions are only defined within the framework of ontological models. So they're not even, they weren't even defined yet in a broader class of realist theories, although in this paper we actually kind of abstractify their definitions in a way that they are defined for non-classical realist theories. Even though we don't yet have a specific non-classical realist theory that we think can do the job, you can nonetheless at an abstract level define what these concepts should look like in these as yet to exist kinds of theories. Okay, so how long have we been going? 48 minutes? So I could keep going. I have some other topics, but this is also a good endpoint. So yeah, what do people prefer? How are we feeling? Are we tired or excited? Okay, I heard more excited than tired, so great. So I'd like to address a few, where do I want to start? So now I'm going out of the order of my talks. And maybe now I can address some specific assumptions that I've been a bit lax on. This is a note to myself because I didn't think I was going to get there today. So I'll start by talking about a hidden assumption that's gone into the things I've said, which is an assumption of linearity. And it's a good assumption, but I want to just be explicit so that it's clear that we're using this assumption. So GPTs live in vector spaces, and that means you can multiply GPT states by real values. You can add them together, and we assume that the ontological representation is a linear map on this vector space structure. So in particular, quantum states, as an example, you can mix them together like this. And something that I assumed kind of in passing was that their ontological representation, well, in general, this whole thing could just be viewed as one operational procedure, right? You could say that there should just be a single probability distribution over lambda associated to this whole quantum state. But I furthermore then went on to write this expression and to say, well, I assume the representation is linear, so I can kind of pull these coefficients out, and we should have that the mixture of the representation of 0 with the representation of 1 with equal weights should be equal to this more general object here. And so why did we assume that? Before I tell you why we assume that, I'll just note that, strictly speaking, operational theories, remember, they're just kind of descriptions of things you're doing in the laboratory. So it's actually quite hard to view them as having mathematical structure, like vector space structure. You can formalize them in such a way that they do have that right structure, but it's a bit complicated, so that's just something to note if you ever get into this stuff in detail. But okay, back to the main point. Why do we assume this notion of linearity? Well, basically, it just follows from the correctness of classical probability theory. So we're imagining, sort of by assumption, a scenario in which the convex mixture of these states of interest is arising because someone has classical uncertainty about which pure state was prepared. There may be other ways to get uncertainty about what preparation was done, like preparing an entangled state and forgetting about half of it. But that's just not the question we're asking right now. We're imagining a case where you have classical uncertainty about what was done in the laboratory. So you have this classical uncertainty can be represented as a kind of ensemble over states with their corresponding probability of having been prepared. And if this is just classical uncertainty, then the law of total probability completely constrains the way that these must be represented. If we want to have some probability distribution over ontic states for this kind of scenario, then the way that has to be computed is it's the probability of a given ontic state lambda given that the state was 1 times the probability that the state was 1, which is just a half, and similarly plus the probability that the ontic state was lambda given the other possible way that it would have arisen, which is the preparation 0, times the probability that the preparation was in fact 0. So this is just the law of total probability, which tells you how to compute the probability of an event A, which can arise in multiple different ways, like conditioned on some events Bn. And so if these probabilities are just a half, we get these two halves, and the probability of lambda given 0 was just what we called mu sub 0 of lambda. So this assumption of linearity is just coming from the fact that, as I mentioned earlier, the ontological models framework uses as its the rules of inference in the ontological models framework are just classical probability theory. And this is exactly the kind of thing you might start to wonder, how do you go beyond classical probability theory if you want to go beyond the ontological models framework? But within the standard framework, linearity just follows. Another assumption, which comes up a lot, is the assumption of tomographic completeness. So what do I mean by this? Well, I mean that if you want to go test non-classicality in the sense of non-contextuality, then you have to start with an operational equivalence, at least one, maybe many operational equivalences. So for preparations, for example, we said these two preparations are operationally equivalent if they lead to the same statistics for all possible measurements. But hold on a minute, what do I mean for all possible measurements, right? For all measurements, in most theories, there will be an infinite set of measurements, and you can't, in practice, you'll never be able to do all possible measurements. So we really mean here, in principle, physically possible measurements, not just the ones you have in your laboratory. You have to consider all possible measurements that any future person with their future technology could do. So this obviously is a difficult thing to test. How do you even know what the scope of possible measurements is? Well, one thing to note is that given a particular theory, like quantum theory or a particular GPT, it's necessary and sufficient to check if the operational equivalence holds for some tomographically complete set of measurements, which by definition, it's a set of measurements that lets you compute the statistics of all other measurements. And so in quantum theory, tomographically complete measurements are actually quite simple. If you just measure the x, y, and z Pauli measurements on a qubit, well, that tells you the x, y, and z coordinates on the Bloch sphere, so it tells you exactly what your density operator is. So now we've at least reduced this continuous infinity of for all measurements down to some finite number. In the case of a qubit, just 3 measurements, binary outcome measurements. So that's a start. It says if you sort of know what your theory is, if you know the scope of the GPT, the dimension of the GPT, et cetera, then you can find some kind of tomographically complete set of measurements. So that helps a lot. But what if you're mistaken about what the theory of the world is, right? We don't want to assume quantum theory. And so how can you ever know that you've really tested all possible measurements and that tomorrow somebody won't find a measurement which which breaks your operational equivalences? So in other words, a mistaken assumption about what the tomographically complete measurements are can lead to incorrect assumptions about what the operational equivalences are, which can then in turn lead to mistaken assessments of non-classicality. So this is a kind of loophole, if you like. And so we need to think about what we can say to deal with this loophole. And you can find examples where you take strictly classical theories and imagine that you happen not to know about measurements along the z-axis. Then this 3-dimensional classical theory will basically be projected down so that the z coordinate always goes to 0, and you end up with some square kind of GPT here, which it turns out you can find examples of this where, for example, it's the 2-dimensional GPT box world, which is highly non-classical. So you start with a simplicial theory. Just because you didn't notice all the measurements in the true theory of the world you suddenly think that you're seeing strong non-classicality. So this is a real problem. If you are wrong about your operational equivalences, then there are many examples where you make the wrong assessment. So how can we ever be confident in our assessment of non-classicality? Well, the point is, just like in all of physics, you can never verify a hypothesis. You can only ever falsify it. So if you think there's an operational equivalence, then you should go do all the measurements you can. Do more and more measurements, try to falsify that claim, and if you fail to do so on more and more measurements, then you start to build up confidence in your assumption of operational equivalence. And it's worth thinking about the case of quantum theory. This is exactly the same way that you go about gathering evidence that we can use density operators to describe laboratory preparations. Right? When quantum theory was first invented, nobody knew that you could just describe this massive macroscopic device just by a POVM element or just by a density operator. Right? It took years and years of people doing every experiment that they could think of, and then they were like, oh wait, there's this much simpler mathematical object that seems to have all the information. Now it's conceivable that tomorrow someone will find a measurement on a qubit which can distinguish between two different mixtures of pure states described by the same density operator. And when that happens, it will be groundbreaking physics because we're all so confident in this particular kind of operational equivalence. So we're essentially in the same boat here. You can gather lots of evidence and you can become quite confident in your assessments of operational equivalences, but you need to do that, otherwise your confidence in your assessment of non-classicality is only ever as good as your confidence in your operational equivalences. Okay, cool. So another topic which comes up a lot, which is how do you deal with imperfect operational equivalences? So I've been using a lot of this kind of simple example where you have a uniform mixture of two preparations is operationally equivalent to a uniform mixture of two others. And I'll call these the target preparations. They're kind of idealized, noiseless. In the quantum case, we often focus on pure states. But when you do real preparations, these are noisy, and they're never going to exactly satisfy the operational equivalences. So in reality, the P1, P2, P3, and P4 that are implemented here, which I've drawn as these kind of green triangles, they're going to be a bit noisy, and they're not going to satisfy this constraint. So the four states that are actually realized in an experiment will never let you meaningfully test non-contextuality inequalities based on this equivalence, because they don't satisfy it. It would be a mistake. Again, if you have the wrong operational equivalences, you can reach the wrong conclusion. But there's a trick that people have realized which lets you get around this problem. So the first trick, there's actually two ways to get around it. The first one says, notice that if you've only done these four preparations, you can nonetheless infer the statistics of every preparation in the convex whole, because GPTs have this convex structure, and the probability rule is linear. And so if I want to know what the predictions for any point inside this gray region are, I can compute them to arbitrary accuracy from the four preparations that I've actually implemented. And so for some of these inferred states, you can pick a set of four inferred states that do exactly satisfy this operational equivalence. So here, for example, if I just pick these blue dots kind of symmetrically far apart from each other, then if I call them P prime, they satisfy the assumed operational equivalence exactly. Now, they're not perfectly pure states and noisy states, but we never assumed that anywhere in our analysis. We just assumed that the uniform mixture of two of them was equivalent to the uniform mixture of the other two. So now we use the statistics not on the preparations we actually performed, but on these inferred states, and we can test non-contextuality for those. So that's one way of using the convex structure of GPTs to enforce the exact target equivalences, even though you never actually did the target preparations. That's fine. All that matters is that the equivalences are the ones you've used in your inequalities. But there's a second approach, which I think is, in some sense, it's a better approach. So one problem with this approach, other than the fact that it's a little bit ugly, you kind of have to do this secondary processing of your data. A bigger problem is that it adds noise, right? In order to find these blue states in general, you kind of have to move everything inwards a little bit. So you're never going to have as large a violation of your contextuality inequalities. In order to test this, you're always losing a little bit of power. losing a bit of non-classicality. The second approach gets around this problem altogether, and it's just kind of a cleaner way of analyzing things anyway. So imagine you've done these same 4 preparations that I mentioned. And the point is, you don't have to target any specific operational equivalences. You could just go to the lab and do whatever you want. Do as many state preparations as you possibly can, and just characterize where they live in the GPT. So if you've characterized that these are your 4 quantum states that you've implemented, and you know they're sort of block sphere coordinates, for example, then you can just compute the actual operational equivalences which hold among them. Don't just assume that they're going to be equal mixtures. Just find whatever coefficients alpha and beta make the mixture of P1 and P2 equal to the mixture of P3 and P4. You can see just geometrically there will be some alpha and some beta for which it's true. The closer you are to your noiseless perfect preparations, the closer these will be to a half. But it doesn't matter what they are. Compute it from the data, and then use that operational equivalence, which holds exactly, to compute your non-contextuality inequalities. So derive your inequalities, which we'll talk about how to actually do that in the final lecture. Or alternatively, forget about inequalities altogether. Sometimes that's a useful way of studying things. But we saw we had this other approach where you just take the GPT representation, find a simplex embedding, or use this linear program to prove that no such embedding exists. And in that approach, you don't even need to talk about inequalities at all. You kind of take the whole structure of the theory, and you compare that structure to the simplicial theories to decide if you have classicality or non-classicality. OK, I think we should end there because it's been an hour. Thank you.